In the very beginning, there was nothing we could call structure. Only an almost perfectly smooth sea of matter spread through the darkness, gas barely warmer than absolute cold, stretched across unimaginable distances. And yet hidden within that smoothness there were tiny imperfections, faint concentrations where there was slightly more matter than elsewhere, a negligible difference, but it was enough. Because the universe has a patient sculptor working without pause for billions of years. Its name is gravity. Where there was a little more matter, the pull was a little stronger. It drew in fresh gas. The more that gathered, the stronger the pull became. Slowly, incredibly slowly, these concentrations grew, drawing matter out of the emptiness around them. So across the young universe, invisible threads began to emerge, a colossal web of gas and mysterious dark matter, which we cannot see directly but feel through its pull. This structure is called the cosmic web. Along its threads, like dew on a spider's web, ordinary matter gathered, the very matter that would one day become stars. Where these threads crossed, the first proto-galaxies were born, loose clouds of gas, not yet resembling the majestic spirals we know today. Dark matter served as their framework, the invisible skeleton around which everything else assembled. Inside these clouds, the first stars of the universe ignited. They were nothing like our sun, enormous, hot, made only of hydrogen and helium, since no other elements existed yet. They burned fiercely and briefly, and with their light they pushed back, for the first time, the darkness that had reigned before them. It was these first stars that began the great work that would never again stop, turning simple matter into complex matter. And then gravity began to bring these galaxies together. Small galaxies pulled toward one another and merged. From dozens of small ones, large ones were born. The large ones gathered into clusters stretching across millions of light years. It is a slow dance, each movement of which lasts hundreds of millions of years, far too long for a human to notice even a single step. But if we sped up time, we would see whole galaxies circling one another, drawing close and intertwining, guided by that same invisible hand. And as the universe matured, it entered its most brilliant epoch. Astronomers call it cosmic noon. That time came roughly 10 billion years ago, when the universe was only about 3.5 billion years old. In that epoch, stars were born at an astonishing rate, about 10 times faster than today. Imagine a sky flooded with the light of young stars. Galaxies closer together, more tightly packed, each one blazing with the birth of new suns. It was then that most of the stars that will ever exist in the universe came into being. Their light, the light of that distant epoch, will keep shining for trillions of years. In that same epoch, the universe shone with another, far more formidable light. In the centers of young galaxies, quasars blazed to life, regions around growing black holes, where infalling matter heated up so intensely that it shone brighter than hundreds of billions of stars at once. Some of these beacons were so bright that we still see them today, their light traveling to us across almost the entire history of the universe. When you look at a distant quasar, you are looking deep into the past, at an age when galaxies were still building themselves. Gravity is the architect of all the great wonders of the cosmos. It gathers gas into stars and ignites them. But the same force that gives stars life also determines how they will end. Because the most massive stars live bright and short. And when their fuel runs low, their cores collapse under their own weight, and some of the most mysterious objects in the universe appear. Black holes. During cosmic noon, they grew more and more numerous, and some of them grew larger, taking in matter equal to the mass of billions of stars. So the supermassive black holes were born, the dark engines at the very hearts of galaxies. They do not simply absorb passively. Around them, matter spins into a searing disk, heating to temperatures at which it shines brighter than entire galaxies. From their poles erupt streams of particles accelerated to nearly the speed of light, jets that pierce the cosmos across thousands of light years. Stars that come too close to such a black hole are stretched and scattered by the very force that once helped them ignite. At the center of nearly every large galaxy, including our own, a giant like this is hidden, quietly guiding the fate of the billions of suns around it. But let's return to the stars, because it is in their lives and their fading that the key to our own existence lies. Most stars in the universe are small. They shine for a long time calmly and in the end fade quietly, causing no upheaval. But about 1% of stars are born massive enough to end their lives differently in a magnificent flash we call a supernova. And here begins the most important part of all. The young universe consisted almost entirely of hydrogen and helium, the two lightest elements. No carbon, no oxygen, no iron, no gold. None of what is needed for planets or for life. All these heavy elements are forged in the depths of stars over the course of their lives under tremendous pressure and heat. And when a massive star completes its journey and flares into a supernova, it scatters all this richness into the surrounding space. Carbon, which will become the basis of living cells. Oxygen, which we breathe, iron in our blood, all of it was once forged inside stars and released by their fading. So a great cycle arises, a cycle of ending and rebirth. From the ashes of vanished stars, a new generation is born, stars and planets rich in heavy elements. Each new generation is a little richer than the last, and with each turn of this cycle, the universe becomes a little more ready to give rise to life. Let's travel now to the outskirts of one ordinary galaxy, our own, the Milky Way. About 4.5 billion years ago here, in a quiet corner of a galactic arm, a cloud of cosmic gas and dust hung in the dark. It slumbered in the darkness until something disturbed its rest. Perhaps it was a shock wave from a nearby supernova. The push rolled through the cloud and set its collapse in motion. Gravity took over, the cloud began to spin to draw inward to heat at its center. Matter fell inward, the temperature climbed, and in the very heart of this concentration, a new star ignited. Our Sun. And around it, from the remaining disk of gas and dust, the planets assembled. Among them, the young, still tormented Earth. The early Earth was not a blue planet with gentle clouds. Its surface was an ocean of molten rock, constantly bombarded by asteroids. The air was thick and stifling, filled with volcanic gases, and acid rain poured from the sky. And yet, deep beneath the waves of the oceans just beginning to form, something began to stir. In cracks on the ocean floor, heat and minerals rose into the water from within the planet. Around these underwater vents, complex chemistry came to a boil, molecules joining, breaking apart, joining again in countless combinations. And somewhere in this process, at least 3.7 billion years ago, the first living cells appeared. Life had begun, but it was unimaginably simple. For nearly 3 billion years, the planet belonged to microbes alone, an entire invisible empire hidden from any eye. No plants, no animals, only microscopic organisms quietly transforming the world around them. And then one of the most important events in Earth's history took place. Some microbes learned to feed on sunlight itself. This process, photosynthesis, gave them energy, but it had a byproduct, oxygen. At first there was little of it, but the microbes multiplied and oxygen slowly, relentlessly accumulated, first in the ocean, then in the atmosphere. For the life of that time, this was an enormous upheaval. For most ancient organisms, oxygen was not a gift but a hazard, a substance they were not adapted to. At the same time, oxygen displaced the methane that it held in warmth, and the planet cooled, sinking into one of the harshest ice ages in its history. Scientists call this the Great Oxidation Event. It happened around 2.5 billion years ago. But what seemed like an ending became a beginning. When the ice retreated, evolution began to accelerate. Oxygen, for all its danger to the old life, carried something precious within it, energy. Organisms that learned to use it gained access to a far greater reserve of power than before, and more energy meant the ability to build more complex, more sophisticated forms of life. After billions of years of solitary existence, individual cells began to unite, first into simple communities and then into unified multicellular organisms. Cells learned to work together, to divide their duties, to specialize. This opened the road to everything that would follow. And when the last of the great ancient ice ages melted away, life seemed to burst into diversity. In a span short by cosmic standards, a multitude of new forms appeared in the oceans, complex, mobile, never seen before. Creatures with eyes, with shells, with limbs, predators and prey, the first beings that actively moved and hunted. This rapid flourishing of diversity was so sudden that scientists gave it its own name. It was the beginning of a path that would eventually lead to fish, to plants on land, to dinosaurs, to mammals, and hundreds of millions of years later to us. It is worth pausing for a moment to realize how much had to come together for this moment to be possible. It took generations of stars that lived and faded, forging the heavy elements. It took a calm orbit at a safe distance from the turbulent center of the galaxy. It took a planet of the right size at the right distance from its star, with liquid water on its surface. And it took billions of years of patient, invisible work by microbes before anything appeared that could be seen with the eye. Not one of these conditions was guaranteed, and yet they came together. So let's step back and take in this whole journey at once. From an almost perfectly smooth sea of gas to the first threads of the cosmic web, from proto-galaxies to the great dance of their mergers, through the dazzling cosmic noon when most of the stars were born, through the lives and fading of massive stars which forged the elements we are made of, to the quiet cloud on the edge of a galaxy from which the sun and earth were born, and finally to the first living cells in the dark depths of an ancient ocean. Every atom of carbon in your body, every atom of oxygen in your breath, every atom of iron in your blood was once forged inside a star that died long before the sun was born. We do not merely observe the universe from the outside, we are made of it. We are the very way in which the cosmos, after 14 billion years, has finally learned to look upon itself. And that perhaps is the most astonishing wonder of all.